Hello everybody. Today we are going to learn in this video torque on a current carrying loop placed in a magnetic field. So here I have shown a loop A, B, C, D. So this is the loop and it is carrying current which is shown by these black arrows. So I is the amount of current which is flowing in the loop. L is the length of the loop and B is its breadth. So it is a rectangular loop, right? And we want to find out what will happen if it is placed in the magnetic field. So for this we will start learning from here that if we have a wire which has a length L and suppose it is kept in a magnetic field B, perpendicular for example, then the force on the current carrying conductor of length L is given by the formula I into L cross B. And this is something we have already learned in our previous video. And we will be using this formula to find out torque on the current carrying loop placed in the magnetic field. Now you all know what is torque. Torque will produce a rotational motion in the loop because there will be two equal and opposite forces, and this is what we are going to learn just now. Now I'm just erasing this. You only have to remember the formula that if the length is L, current is I and the magnetic field is B, then force acting on it is I into L cross B. So I'm just removing this and we'll find out how to find out the torque on the loop. Now consider the arm AB. So force experienced by the arm AB will be I into length is L cross magnetic field is B. We will now substitute the directions for L and B. The direction of L will be taken as negative of J because current is flowing downwards. So I will write down minus L into J cross. B is positive x-axis. So I will write down B with I cap as the vector. Now my current I remains the same as this. L and B can be taken out. This is a negative sign. So I have minus J cross I inside the bracket. And minus J cross I, you know, is nothing but, this is nothing but K. So ILB into K cap is force on the arm AB. It means that on this arm AB, there is a force in this direction, which I am showing right by my pen in the outward direction. So this is one thing. Now we will want to find out what is the force on the arm BC. So on the arm BC, because the length B is parallel to the magnetic field B. Hence when the length is parallel to the magnetic field, we have a cross product. So we will write down I as the current. L cross B can be written as LB sine. And this is theta, LB sine theta. The angle between the length and the magnetic field is 0. So I will write down I B into B because my length is B now. So I B into B sine of 0 degree, which will give me 0. Now you can see that for the section CD of the loop, the current is opposite to AB. And the rest things are same. The magnetic field is in the same direction. Hence, if the force is in the K direction like this outwards for the arm AB, it will be into the plane of the board for the arm CD. So I will write down force on the arm CD will be IL into B. The magnitude will be same, but the direction will be opposite, so it will be negative of K. Similarly, if we talk about DA, it is again a case which is carrying a current opposite to the one carried by BC. So for this, we will have not sine 0, it will become sine 180 because the current and the magnetic field are anti-parallel to each other. So they make an angle of 180 degrees. Hence the force on the arm AD will become again 0. So you can very well see from this here that force on the arm AB is in the forward direction. Force on the arm CD is into the plane of the board, that is in negative Z direction, and the force experienced by this arm and the force experienced by this arm is 0. and we have taken a very, very simple case in which the coil is lying on this board like shown, I have shown over here, and the magnetic field is perpendicular to it like this. So in this case, if one force is coming outward and the other one is going into the plane of the board, then I have a case which can be shown like this, like this. This is the distance from this point to this point. I will show it again with a different color. So this is B. One of the force is outward and the other is into the plane of the board. So what will happen? The coil would want to rotate about this axis. So it is almost like this. This arm wants to come out, and this arm wants to go into the plane of the board. So this phone will rotate about an axis which will be passing through the midpoint. So this will rotate like this. Hence these two forces will constitute a couple, and a couple will always exert a torque. And how much is the torque? We have already done this in our 11th standard. Torque is always measured as either of the force into the force arm. And what is the force arm? It is either of the force. Force is ILB. So I will write down ILB. And force arm is the perpendicular distance between the two forces. The perpendicular distance is small b. So I will write down b here. Now L into B is nothing but the area of this rectangle. So I will write down IAB. Hence, for this coil, the torque that will be exerted by the magnetic field will be equal to I into A into B when the plane of the coil is as shown here on the board, that the area vector. Now what is an area vector? Area vector is a vector which is perpendicular to the area. Now what you have to do is you just have to hold the whole loop in your right hand in the direction of current like this. So the outward normal is my thumb, and this is the direction of the area vector. So when the area vector is normal to the magnetic field, right? When the area vector is normal to the magnetic field, or you can say when the coil lies in the plane as shown over here, then the torque is equal to I into A into B itself. Now this is a very, very simple case. This is case number 1. We want to learn what if the plane of the coil makes some angle with the magnetic field. So I will just erase this. You only remember for this case the torque was equal to I into B, and also understand that this coil wants to rotate about this axis.